Hello student, welcome to our physics discussion. So we continue like we have done in the last class, last video that you have seen. We continue with our discussion on degree of freedom. Degree of freedom. Degree of freedom. And already, as you know, we have discussed the degree of freedom of a monoatomic gas because a monoatomic gas, there we are trying to link degree of freedom with the number of coordinates. So monoatomic gas is just like a mass particle, just like a point mass, and a point mass has got only three coordinates. One is x, other is y, and third is z. Its velocity, momentum, energy, all can be resolved along x, y, and z. So we forget all those things. We let us say, so for the timing, we focus on the coordinates. So a point mass, just like and like that, a monoatomic gas has got only three coordinates. Its position can be expressed in terms of three coordinates. So thereby, degree of freedom for a monoatomic gas is equal to 3. That was our idea. That was our discussion. Now, from the monoatomic gas, we extend our idea to a diatomic gas. Diatomic gas, as you know, it consists of two molecules. You can refer to the diagram that I have drawn. Let us say our diatomic gas is there. So far as diatomic gas is there, and you know, usually because it consists of two atoms, the molecule consists of two atoms, the two atoms must be bonded by a molecular bond that we discuss extensively in chemistry. And sometimes we talk about that ionic bond, covalent bond, all those bonds, single bond, double bond, triple bond. But when somebody goes through the 11th and 12th chemistry, he or she gets a very strong idea on the bonds and all that. So thereby, as the diagram referred, as you can refer to the diagram, the two atoms are there, atom number 1, atom number 2 at the right, bonded by a chemical bond, which is represented by the letter L. L is the length of the bond. So if you now try to find the degree of freedom of the diatomic gas, we know our exercise will be just to find out the number of independent coordinates. The first atom, it can enjoy three coordinates, x1, y1, z1. So thereby, we know for the first atom that is 3. The second atom, we can also see, a student can say also it enjoys three coordinates, x2, y2, z2. So thereby, a student will be tempted to say that degree of freedom equal to, if you add the number of coordinates available, that is 3 plus 3 equal to 6. But no, we have to be careful. Just look at the thing. It is the degree of freedom should be taking into account of the independent coordinate, not the dependent one. If our molecular position, if the bond is parallel to x-axis, the way I have shown it to make it more clear to you and to make it more simple to you, you know, at a particular condition, under a particular chemical condition like temperature and all those things, the bond length is constant. This molecule, this atom, or the left side atom has got a x coordinate x1. The right side atom has got a x coordinate that is x2. And x1 and x2, they are not independent of each other. They are linked with each other because we know that x1 plus bond length equal to x2, or the difference of the coordinates equal to them. So that is the link between x1 and x2. So x1 cannot be independent of x2, or x2 cannot be independent of x1. So thereby, so far as two y coordinates are concerned, so we have to refresh our ideas. So far as two independent y coordinates are concerned, this can go up, that can go down, they can have two independent y. So far as two independent Z axes are concerned, these two atoms they can enjoy two independent Z. But so far as two independent X is there, they have to have only one X because both their X's, X1 and X2, they are linked with each other. They do not have got independent X. So 2 plus 1, we know the answer will be equal to 5. So diatomic molecule must be having a degree of freedom or should be having a degree of freedom equal to 5. I think I am clear to, but sometimes it may be too cumbersome, rigorous to find out all those things. So thereby, for normal temperature and pressure, you must mark my words, for under normal conditions, there is an empirical formula to find out the degree of freedom. There is an empirical formula to find out the degree of freedom for a polyatomic molecule. We got the formula that says the degree of freedom of a molecule will be equal to, should be equal to 3A minus B, where A is number of independent coordinate, number of independent coordinates. Hey, sorry, I'm sorry, I have to revise. That is not number of independent coordinate. That is number of atoms in the molecule, number of atoms in the molecule. Let me remove this also. And B is number of independent relationships that exist between, or those exist between the atoms. My marker doesn't cooperate with me. If somebody makes it simple, all those high faulting words can be replaced by very simple term, that is number of bonds. Number of bonds available in the molecule. Number of bonds. So thereby degree of freedom, we express it, or the formula says that is 3A minus B, that is the formula, where A is the number of atoms, and because each atom has got a unique X and unique Y and unique Z coordinate, so the first term is 3A and minus B. Minus B is number of independent relationships which exist between atoms, or very simply number of bonds. But mark my words, in chemistry sometimes we see a bond that is a single line, that is single bond. Sometimes the bond is a double bond, and sometimes the bond is a triple bond. A bond is a bond. In physics, we should not give single bond the value 1, double bond the value 2, and a bond is a bond. Bond is whether it's a single bond or double bond or triple bond. They may be having their chemical significances, but from the point of view of physics, they are one. A bond is one. It may be a single bond, the bond value equal to 1. It may be a single bond, double bond. Right? So if in that case, let me, because we need to remove some, create some space, because that has been written. Anytime you can refer to it. So if you go for a monatomic gas, For a monoatomic gas, monoatomic, if somebody tries to find degree of freedom, then degree of freedom, we know that is 3, number of atom equal to 1 minus, because the atom cannot form bond with itself. So there is no bond. Without the presence of 2 atoms, we cannot think of a bond. So for a monoatomic gas, that is 3. If you go for the next thing, that is diatomic. For a diatomic gas, we know degree of freedom must be equal to number of atoms, 3 into number of atoms equal to 2 minus, between the 2 atoms, we can think of only a bond, maybe a single one, double one, triple one, doesn't matter. So number of bond equal to 1, so 6 minus 1, that is equal to 5. If you go for a triatomic gas, and for triatomic gas, we are having complications. Gases like carbon dioxide on those. Of course, I should not talk big, I should not talk longer. Otherwise, my bad knowledge of chemistry will be coming out. So far as my knowledge goes, and that dates more than 30 years back. Carbon dioxide, we know the structure is like this. If the structure is like this, there are only 2 bonds. There is no bond between O and O. So thereby, we know here degree of freedom will be equal to, that is 3 into number of atoms. That is 3 minus the number of bonds equal to 2. That will be 7. But sometimes in a triatomic case, all the 3 atoms are well bundled with each other. That happens in the case of epoxy oxides. So thereby, we know the molecular structure is like this. So thereby, our answer will be, degree of freedom will be, that is 3 into 3, that will be equal to, minus number of bonds equal to 3, that will be equal to 6. So a triatomic gas can have a degree of freedom that is 7, or can have a degree of freedom that is 6. So now triatomic gas becomes controversial until the question clarifies it. We cannot get a definite degree of freedom. Okay, so usually, as you can see, your questions and most of the examples that you get in this topic will be dealing with a monoatomic gas or a diatomic gas. Triatomic gas are very, very rarely given. So that is the degree of freedom. Okay, and the thing is that the degree of freedom also has got many kinks. Okay, so degree of freedom, as I told you, has got many kinks in it. I pause the video for the timing to clear up all the space and all that. So as I told you before in the last video, we are taking the help of half truth. And here I try to explain the idea of the degree of freedom with the help of coordinates. But in fact, the degree of freedom is not exactly so. The degree of freedom, if somebody goes for the exact definition, exact idea, then that should be like this. The degree of freedom of a molecule is the number of ways a molecule can have its energy, stored energy. It can be in the form of kinetic energy. And kinetic, when somebody talks of kinetic energy can be translational or linear kinetic energy, and rotational kinetic energy also. Also, the molecule atoms are liable to vibrate, and the molecule is bound to have vibrational energy. So when somebody talks of degree of freedom, usually that is the number of ways in which a molecule can store its energy, that is kinetic energy. And when you talk of kinetic energy, that is translational kinetic energy, and rotational kinetic energy. Rotational kinetic energy, you have to take the stock of everything, plus vibrational energy. Vibrational energy, vibrational energy. So total number of ways the molecule stores of the energy is equal to the degree of freedom. Let us consider a monoatomic gas. A monoatomic gas, we know because it's a single atom, we cannot think of rotational kinetic energy because a molecule is just like a point mass. It has not got sufficient moment of inertia, mass moment of inertia, and a molecule has got nothing to vibrate. You cannot attach a molecule to something. So there is no question of any vibrational kinetic energy. And because the rotational kinetic energy is negligibly small due to very small contribution towards mass moment of inertia, so molecule has got only translational kinetic energy, a molecule, monoatomic gas, mark my words. It has got X kinetic energy, Y kinetic energy, and Z kinetic energy. If you divide its velocity or its kinetic energy into three components, so thereby degree of freedom for a monoatomic gas was equal to 3. For a diatomic gas, we know diatomic gas that is like this. We do know this atom as a whole can have 3 translational kinetic energy. 3 translational kinetic energy plus when we talk of rotation and vibration, we know the molecule can rotate about this axis. The molecule can rotate about an axis which is passing through this, and the molecule now can have substantial moment of inertia because the masses, they are not passing on grid. The masses, they are not passing on. So this a diatomic molecule, as a whole, a molecule has got 3 translational kinetic energy plus 2 vibrational kinetic plus 2 rotational kinetic energy plus vibrational kinetic energy. But there is a serious difficulty that has to be resolved with the help of quantum mechanics. Due to that, I have taken the course of explaining to you the idea of degree of freedom with the help of coordinates. Because as a 11th and 12th student, you do not have got a very serious idea of quantum mechanics. Here, there is a term which says, which is, just a minute, quantum mechanical freezing. Quantum mechanical freezing. That is, if let us say you take the degree of freedom, you try to count the degree of freedom, taking the things properly without taking coordinates, we try to find out in how many ways a molecule can store energy, in how many ways the molecule can store its kinetic energy and vibrational energy. But in reality, you won't be getting that because quantum mechanics prohibits sometimes, it prohibits some certain degree of freedoms. That is due to temperature and all those things. The issue is quite complicated. So due to quantum mechanical freezing, so degree of freedom that we normally calculate using our simple arithmetic and all that is not exactly as it is shown by the molecule. So for example, hydrogen. We know hydrogen is a diatomic gas. But if you take a temperature that is nearly 50 or 60 Kelvin, At that time, we know hydrogen, in spite of that, it's a diatomic gas that behaves as a monoatomic gas and gives us degree of freedom equal to 3. So the formula that I have given you is an empirical formula. The degree of freedom equal to 3a minus b. That's a very simple formula. It's okay, no problem. But that is for normal temperature, pressure, all those conditions. Those are not for extreme conditions, just like I told you, hydrogen equal to hydrogen at 60 Kelvin, which is a very, very low temperature. So the issue of degree of freedom is a bit complicated. That has got a serious involvement of quantum mechanics in it. But to have a basic idea of degree of freedom that I have tried to convey to you, that is like this, and you have to wait for your upper classes or to promote yourself to the upper classes where you will be getting the full idea of quantum mechanics and the issue of the degree of freedom, right? And the work of some great men like Einstein and all those things, in it. Okay. So thank you. At present, our degree of freedom idea is just like this. We depend on our formula that degree of freedom equal to 3a minus b. Will be extending our idea of degree of freedom, will be utilizing the idea of degree of freedom in our future videos, which will be coming shortly.